Alright, so in this video, I'm gonna be explaining another important article with the title self-reg, self-supervised contrastive regularization for domain generalization. This paper in 2021. In general, an experimental environment for deep learning assumes that the training and test dataset are sampled from the same distribution. However, in real-world situations, a difference in the distribution between two datasets, domain shift may occur, which becomes a major factor impeding the generalization performance of the model. The research field to solve this problem is called domain generalization, and it alleviates the domain shift problem by extracting domain invariant features explicitly or implicitly. In recent studies, I have a playlist for contrastive learning that I talk about traditional contrastive learning and modern. In modern contrastive learning, we only care about positive pairs for several reasons. So, in recent studies, contrastive learning-based domain generalization approaches have been proposed and achieved high performance. These approaches require sampling of the negative data pair. However, the performance of contrastive learning fundamentally depends on quality and quantity of negative data pairs. That's why people shifted to positive data pairs only. To address this issue, we propose a new regularization method for domain generalization based on contrastive learning, self-supervised contrastive regularization. The proposed approach uses only positive data pairs. Thus, it resolves various problems caused by negative pair sampling. Moreover, we propose a class-specific domain perturbation layer which makes it possible to effectively apply mix-up augmentation even when only positive data pairs are used. So you see, our model utilizes the self-supervised contrastive losses for the model to learn domain invariant representation by mapping the latent representation of the same class sample close together. Note that the different shapes, circles, stars, and squares indicate different classes. And we differentially color code according to their domain. So we have these three classes, C1, C2, C3, and we have these domains, D1, D2, D3, D4. So there is a self-regularization from them to each other. We start on motivating our method before explaining. The main goal is to learn domain invariant representation from multiple sources. Here we propose a self-supervised contrastive losses to regularize the model to learn domain invariant representation by mapping the representation of the same class samples close together, while that of different class samples further away in the embedding space. This may share a similar idea with contrastive learning. So you got the idea. We have this feature, we have two network FC and F theta and FC. Here is our regularization block. So we propose the self-supervised, which is in batch contrastive losses, to regularize the model to learn domain invariant representations. These losses regularize the model to map the representations of the same class samples close together in the embedding space. We compute the following two similarities in the embedding space: individualized and heterogeneous self-supervised dissimilarity losses. We further use stochastic weight average technique and in the interdomain curriculum learning to optimize. In curriculum learning, you can use the technique of active learning as well. But curriculum learning, we assume that everything is labeled. You just need to find hard examples and train on them based on the uncertainty, which is the probability of prediction. So individualized in-batch dissimilarity loss. The dissimilarity between a positive pair of the same class is measured like this. This Z is randomly chosen from other in-batch latent representation that has the same class C. So it's a latent representation. We only consider optimizing the alignment of positive pairs and the uniformity of the representations. Oh, by the way, in contrastive learning, there are two important performance measures: alignment and uniformity. So some papers are here, some papers are here. So there is a trade-off between alignment and uniformity. For example, if it is hypersphere, if these are positive pairs are near each other, it's alignment. But on the other hand, we want all of them to be distributed, so it should be uniform as well. You see an overview of the proposed self-supervised contrastive regularization losses. In CDPL, we have this latent variable, and then they are shuffled, they are mixed up, and we have this loss that we will talk. This loss which is we compute the heterogeneous in-batch dissimilarity loss. So to further push the model to learn domain invariant representation, we use an additional loss called heterogeneous in-batch dissimilarity loss. Given latent representations from the previous step, we apply a two-domain mixed-up layer to obtain the interpolated latent representation Z sub I across different domains. This regularizes the model on mix-up distribution, for example, a convex combination of samples from different domains. This is similar to a layer proposed by Wang in this reference, like this, that gamma here is just we draw it from beta distribution. And U sub j is randomly chosen that have the same class label. And gamma is controlled by hyperparameter alpha and beta. So finally, we compute the heterogeneous in-batch dissimilarity loss. The proposed individualized and heterogeneous in-batch dissimilarity losses can be applied to both the intermediate features and the logits from the classifier. We use the loss function like this, where we use this lambda feature and lambda logit to control the strengths of each term. So we use the following loss function that consists of classification loss as well as our self-supervised loss. Stochastic weighted average is an assembling technique to find a flatter minimum in loss space. And by averaging snapshots of model parameters derived from multiple local domains, local minima in the training procedure. It is known that finding a flatter minima guarantees better generalization performance. And thus, it has been used in domain adaptation and generalization fields that require high generalization performance. So given model weight space, where n is just a number of training steps, There is no specific constraint for sampling model weights. However, in general, sampling process is performed at a specific period while the model is sufficiently converged. We use Z as a cyclic step. And sample weight space for SWA. Note that we use SWA to examine whether the proposed method is compatible with other existing techniques.